So we're going to go over the material of week 5 for our discussion, and we're going to start with the review material for Calc 1 and Calc 2. So the first thing is we want to do a couple of differentiations. So we want to take the derivative of arctangent of 5 over x. We have to take into consideration, so first of all, arctangent is what people also denote by tangent to the -1. And the derivative of arctangent is a rational function. Arctangent of x has derivative 1 over x squared plus 1. So by applying the chain rule, we will get 1 over 5 over x squared plus 1. So we think of this as arctangent of y, and the derivative of arctangent of y is 1 over y squared plus 1, and we need to take the derivative of 5 over x. And the derivative of 5 over x is -5 over x squared. Actually, it's kind of fun to try to simplify this slightly. So let's see how it, we can leave it like that, but if we want to use it, then we better simplify it. So we will have a -5 on the top. And on the bottom, we have what? So you have a 5 square over x squared plus 1, which is multiplied by x squared, is what is going on. And this can simplify as -5 over 5 squared plus x squared. Okay, let's go to the next differentiation. So we want to differentiate ln of x squared plus 1 times sine of 3x plus 1. So here we have the product rule along with two applications of the chain rule. So what is the derivative of ln of x squared plus 1? So the derivative of ln of x squared plus 1 is 1 over x squared plus 1 times 2x. That's a classical application of the chain rule. And we want to multiply this by sine of 3x plus 1. So the derivative of the first times the second, plus the first times the derivative of the second function of sine of 3x plus 1. And what is the derivative of sine of 3x plus 1? That would be cosine of 3x plus 1 times 3. And that's it. Now we have a couple of integrals. So we have the integral of 1 over x squared minus 1. This is a standard partial fraction decomposition where you take 1 over x squared minus 1, you write it as 1 over x minus 1 times x plus 1, and then you want to write this as a over x minus 1 plus b over x plus 1. You multiply all sides by x minus 1 times x plus 1, and that gives you 1. Sorry about this. 1 is equal to a times x plus 1 plus b times x minus 1. And here, this thing is to set x equals 1. If you set x equals 1, then what you get is 1 is equal to 2a, a is equal to 1/2. And if you set x equals to -1, then you will get 1 is equal to -2b. So b is equal to -1/2. So this means that, oops, sorry about this. Let's clean it up. This means that the integral of dx over x squared minus 1 can be written as the integral of 1/2 of 1 over x minus 1 plus or minus, if you like, the integral of 1/2 times 1 over x plus 1 dx. And these are two easy integrals, I guess. 1/2 ln of absolute value of x minus 1 minus 1/2 ln of absolute value of x plus 1. Don't forget the plus c, and that's all there is to it. Now, the next integral is kind of fun. It's the secant, the integral of secant. And this is pretty much an integral that you need to remember. I mean, if you rely, if you find this somewhere and you rely on having a method to actually compute it, either you already know the answer, or it will take you a little while to figure out the answer. So that's going to be ln of tangent x plus secant x. And you know what? In some books, you will find the outrageous statement that in order to compute this integral, you have to use the substitution u is equal to ln of tangent x plus secant x. I mean, that is actually true. Anytime you have an integral where the answer is eventually ln of something, you can use that as a substitution in order to find this integral. But this is, kind of silly. I mean, who would ever come up with this substitution? I mean, you basically know the answer if you are going to use the substitution. So, of course, one would argue, is there any natural way of computing this integral? And look, it's a long computation, but I'm just going to show you the beginning so as to show you that, yes, there is a conceptual way of doing this. And the conceptual way is to think of secant as 1 over cosine, and then write this as cosine x over cosine square of x. And then I write this as cosine x over sine square of x. I'm sorry, 1 minus. So 1 minus sine square of x. And then apply the substitution u is equal to cosine x. I'm sorry, u is equal to sine x, and du will be cosine x dx. And this will end up being du over 1 minus u squared, right? Which is pretty much the integral that we just found, right? So we have it up there. That was u squared minus 1. So, why don't we do it after all? Why don't we finish it? So since this is minus the integral of du over u squared minus 1, I can now copy it, and this will be negative 1/2 ln of absolute value of u minus 1 minus 1/2 of ln oops, my pad is not cooperating. Okay, now it does. Ln of u plus 1 plus c. And now you can, sorry, this is plus. And you can write this as 1/2 ln of u plus 1 over u minus 1 plus c. Now what you do here is you can actually rewrite this as 1/2 ln of what was u? U was sine x, so sine x plus 1 over sine x minus 1. It seems that we're doing the whole thing after all. And this will be equal to, now you multiply above and below by sine x plus 1. So this is 1/2 ln of sine x plus 1 squared. And on the bottom, you will have sine square of x minus 1. And this is 1/2 ln of sine of x plus 1 all squared. And the bottom is really minus cosine square of x. But you are inside an absolute value, so none of this matters. So you can get rid of the sine, and you can also take the square outside. So this will be sine x plus 1 over cosine x all squared. And now this cancels out with that, because you can always take the factor in front of the ln as exponent. And pretty much you have to ask yourself, what is ln of, what is sine x over cosine x, and what is 1 over cosine x? And you will get this. So actually we did the whole thing, right? So now you know how we get this integral in a conceptual way. Okay, enough with that. Let's go to our material from our multivariable course. And the first thing that we want to do is look at two exercises with lengths of curves. And we have the length of the trajectory of r of t is equal to t cubed plus 1, 2t cubed minus 3, and t cubed from t equals 1 to t equals 2. Let's see what we get here. So we get r prime of t is equal to 3t squared and 6t squared and 3t squared. And of course, if we take the absolute, the magnitude of this, that would be square root of 9t to the 4th plus 36 t to the 4th plus 9t to the 4th. And what we have is 9 plus 9 is 18 plus 36, that's 54. So we're going to have square root of 54 times t squared, which is the square root of t to the 4th. Right, so that should be pretty straightforward to integrate. So we will have the integral from 1 to 2 of square root of 54 t squared dt, which is going to give us 54. Square root of 54, and we have t cubed over 3 from 1 to 2. That will be 8 minus 1, also known as 7. So this will be square root of 57 times 7 over 3, or something along those lines. I mean, the bottom line is that we were able to actually simplify the formula for the magnitude, and that is what is always going to be the main issue here. The truth is that if you look at this equation is a little misleading in the sense that you might look at it and think to yourselves, well, what kind of curve is this? And actually, it's a straight line. It's a straight line because the only thing that appears here is t cubed. So you would actually traverse the same thing if instead of t cubed you had t in there. So that's what makes the whole computation possible and actually, at the end of the day, quite simple. Let's go to the second computation. So for the second computation, we need to find the length of the trajectory of r of t equals e to the t, comma e to the negative t, comma square root of 2 times t, from t equals 0 to t equals ln of 2, and we want to express the answer in the form a over b. So this exercise invites you to actually simplify this as much as possible. Okay, so what do we do here? So again, we need to find the velocity, the derivative in other words. So this will be e to the t minus e to the negative t and square root of 2. We need to take the magnitude of the velocity. Remember, which is the speed. It's the integral of the speed that gives us the length of the trajectory. So this will be square root of e to the 2t plus e to the negative 2t plus 2. And now the idea here is kind of simple. There was a homework problem. I saw people going to cosine hyperbolic and things like that, which are still doable and correct. But here there's a very simple idea, and it's based on the very simple identity a plus b squared is equal to a squared plus 2ab plus b squared. So if you have the sum of two squares of two numbers and the double product of them, then that's a perfect square, and that's what we're after here. Because the first one, we can write it as e to the t all squared. And the last one, if I want to match it completely, we can write it as e to the negative t all squared, meaning this one right here, right? How about the 2? The 2 is the fun part. This can be written as 2 times e to the t times e to the negative t. Why? Because e to the t times e to the negative t is equal to 1. Okay, so we're pretty much come up with this pattern, and this will give us e to the t plus e to the negative t squared. And we take the square root of that, and of course, square and square root cancel each other, and you get e to the t plus e to the negative t. So now finishing the problem is quite straightforward. You will take the integral from 0 to ln of 2 of e to the t plus e to the negative t dt. So this will be e to the t minus e to the negative t. That's the antiderivative from 0 to ln of 2, which will give you e to the ln 2 minus e to the negative ln 2 minus e to the 0 minus e to the negative 0. Now, this is 1 and this is 1, which means that this whole thing is 0. E to the ln of 2, by the definition of logarithm, is actually 2. And the fun part is, what is e to the negative ln 2? I will remind you that this is 1 over e to the ln 2, meaning it's 1/2. So the whole thing is just 3/2. And that completes the problem. We did our simplification the way we were supposed to. And it's a good idea to always remember this little trick that can be used in cases like this. Okay, let's go to the next problem. For the next problem, we need to find, to sketch the domain of definition of the function f of xy is equal to square root of x squared plus y squared minus 16. And to do so, we just need to take into consideration that the domain is going to be simply all x and y's for which this formula makes sense. What do we need to ask of this formula to make sense? I mean, we have just square roots of non-negative numbers. So we need to ask that x squared plus y squared minus 16 is greater than or equal to 0. So here, there's a standard way to sketch such things. You begin by sketching the curve that is obtained by replacing the inequality with equality, meaning x squared plus y squared is equal to 16. And that's what? That's a circle of radius 4, right? We know in general that the x squared plus y squared, the equation x squared plus y squared is equal to r squared gives us a circle of radius r. So this is a circle of radius 4. And now we have to ask ourselves, what part of it is the domain of definition? Is it the interior or is it the exterior? And for that, we can just test a specific point to see where we fall. If you test 0, 0, you will see that it fails the test. It doesn't satisfy this inequality because you get negative 16 is greater than or equal to 0, which is not correct. So the domain of definition is the exterior. And the thing that I want you to realize here is that the boundary of this domain is also part, the boundary, meaning the circle itself, is part of this domain. Let's go to the next problem, which asks us to sketch the level curve of f of xy is equal to x plus y squared associated to the z value 1. What does this mean? By definition, the level curve, or rather the level set, is all the xy's for which the function has a specific value. And in this case, it is specified that that value should be 1, right? So it's all xy's for which x plus y squared is equal to 1. And now pretty much you're back to pre-calc and ask yourself, what does this equation represent? And the best way to understand it is to write it as x is equal to minus y squared plus 1. Because you can think now as of the x-axis as the axis of the y-axis as the axis of the independent variable, and the x-axis as the axis of the dependent variable. So if you have minus y squared would have looked like this, something like this. You have plus 1, which means you transfer it to the right, and pretty much your curve will look like this. So it's a parabola whose axis is the x-axis, it points to the left. So if you were to switch the roles of x and y, that would mean downward. So to the left is the negative direction in the horizontal sense. And you just need to transfer it by +1, which is dictated by this. So this is your level curve. And what is interesting to see is if you took level curves for this function for other values of z, you would get pretty much similar parabolas shifted to the left or to the right, depending on what the z value would be. Last but not least for today, we want to have the limit as xy tends to 0, 0 of 2xy over y squared plus x squared. To this end, let's actually, it's very, we want to show that this limit doesn't exist by using the two-path method. And I think here it's very convenient to define the function f of xy to be 2xy over y squared plus x squared. What does it mean to use the two-path method? It means that we're trying to approach 0, 0. We'll try to approach it in two different ways. And those two different ways are going to give us different feedbacks for the outputs of the function, rendering it impossible for the limit to exist. That's the idea of the two-path method. So for example, if we take f of t, 0, which means we proceed along the x-axis, we will get 2 t times 0 over 0 squared plus t squared, which is really 0 over t squared, and this is equal to 0. So that tells you that the function is constant along the x-axis and it's equal to 0, which means it approaches 0, it's already there. But now, if you take f of t, t, then this will give you 2t times t over t squared plus t squared, which is 2t squared over 2t squared, also known as 1. So that tells you that along the bisector, so this is where this is the trajectory, if you like, of the vector valued function r of t is t, t. And along this line, the function is constant and equal to 1, which means that if you try to approach the point under equation along this line, you get the impression that the limit has to be 1. Unlike the case where you were approaching along the x-axis, where you thought that the limit was 0. So that discrepancy, that difference tells you that the limit doesn't exist, and that's precisely the point of the two-path method. So by the two-path method, the limit does not exist. And that's pretty much the end of our session for today. Thanks for watching.